Okay. So, yeah, before we start, so this week two presentations. One is this Atari video game playing. Are you guys ready? Who's presenting? Manoj is here. Virendra Patel and Mayank Shukla. No? Do you know if they are continuing in the course? How about diffusion models? That you are ready to present? Okay. So mail me the presentation. But this, anybody knows if they are still in the course? No, you don't know. Okay. Yeah. So he has left, he is left, he is left. You are the only one, huh? I see. So keep your presentation ready. We'll see how today's lecture goes. Maybe we'll, But if you can do it in next class, which is on Thursday, we'll do it. Otherwise, we'll do it next week. But be ready for Thursday. Okay? I see. So they have probably dropped out the course, huh? Fine. Okay. So yes, we talked about the environment and the agent. And this agent takes an action and it interacts with the environment through the action. It gets a reward at every time step. And we model the environment as having states. So for example, when we talk about a video game and we talk about the display of a game, whatever you show on the display is the state of the environment. Right? It can change from one display to the other. So that is modeled as a state of the environment. So once the agent takes an action, because of that action, the state of the environment changes. So it gets to the next state. So an agent interacting with an environment which provides a reward signal, and our goal is to learn how to take actions to maximize the reward. So that's our goal. The key thing is, rewards may not be known in advance before you play the game. In machine learning, we know the data, we know the labels, everything we know. Here, whatever rewards come, we may not know in advance. We may know a probabilistic model for the reward. So the rewards may be stochastic. They may come from, let's say, a normally distributed random variable or multiple such distributions, or they may be deterministic, but still, they may be known or they may not be known also. So in such a situation, how do you learn? Right? So something to think about. So let's look at an example. This is a cart pole example. So here is a cart and the agent sits in the cart. What can agent do? Apply a force in a particular direction for the cart to move. So it can apply a force in this direction, and once it applies a force, the cart will move in that direction, it will accelerate in that direction. The state of the environment, the feedback it gets from the environment is this angle theta, which this lever makes from the perpendicular line. Okay? Angle. Also the angular speed, the rate at which it is falling down or going up, and the position and the horizontal velocity. So 4 state variables. Horizontal force is one state that you apply, one variable that you get. And reward could be 1 at each step if the pole is upright. If it falls down, the reward becomes 0. Okay? Your objective is to balance the reward. Now, in this problem, we may not even feed the laws of physics inside. Right? So, without the laws of physics, agent has no information as to which action is going to lead to what future states, and also what will be the reward in that state. Right? So it is unknown. It has to learn from this particular setup. And how does it learn? It learns by exploring the environment. It can do some action. And then it observes, because of action, what reward I get, how the state changes. And keep trying. And slowly, over a period of time, it can build its own worldview, world model for the world, and then from that it can learn. Okay? Another example, robot motion. how do you make a robot move forward? Right? One option is that you can actually look at all the joints, look at all the weights, look at the terrain, give all those information to the model, create very carefully drafted, equations of physics, of laws of motion and all, and then ask the robot to do a maneuver or walk. The problem with this thing is that, you have friction, you have some other unknown. So the thing is, you cannot know the laws or the exact motion. You would know it to approximation. And then if you don't know the exact, so you say apply this force, the arm will move in a particular way. But in reality, you kind of know the trajectory, but exact movement may depend on environmental factors also. So you may not know the exact movement of the arm. And then now you have a difference from the theoretical model to the actual, movement of the arm, then how do you correct it? So a better approach would be to, learn from the environment itself. Okay? So your state here is angle and position of the joints. Action is torque that you apply on the joint. And let's say if you want the robot to learn to walk, then the reward for each positive movement, right? One step movement every step. Okay? And this is an example of, famous Atari games. So you play the game, your input or the state of the environment is the raw pixel from the game state. Your movement are left, right, up, down. Reward is, score that you have in the game. Okay. Similarly, other game playing like the game of Go. Right? So objective is to win the game. State is position of all the pieces. Action is where to put the next piece. And reward is 1 if you win the game at the end. And so there is no intermediate reward here. In the previous example we had Atari game, at every step you have a game score. Or when you're looking at balancing a ball, at every step you have a reward. Here you have reward only at the end. Okay. So the key characteristics is there is no external supervision, all data driven, discrete time steps. And what we assume is that the reward comes later, right? So it's delayed by a time step, right? You take an action right now and the reward will come later. And action, they also impact the state. So here's the environment, here's the agent. You take an action, the state changes, it leads to a reward, and then finally you observe the state in the reward. This is inspired by neuroscience because, if you look at this famous Pavlovian experiment in classical conditioning, right? They put a dog, they gave some food to the dog, and they observed that when the dog saw the food, it began to salivate. But before they gave the food to the dog, a few seconds before that, it accidentally happened that a bell would ring. And what Pavlov observed was that even when the food was not there, just the ringing of bell, after some time, the dog will start salivating in the anticipation of food to come. So basically, you make some observations, and based on these observations, the state of the environment, you take an action, and then it leads to a reward. And you keep applying that cycle of observation, action, reward, and from that you learn. And we learn, in this case, in the case of a dog, the dog learns that whenever the bell rings, the food is going to be there, so it begins to salivate. This is a subconscious process. So if you look at the machine learning areas, we talked about unsupervised learning, where we talk about clustering, dimensional reduction, generative models, and supervised learning, regression classification typically, and reinforcement learning is the third branch. It has single agent, multi-agent, and various other stuff. We are going to just cover a very brief overview of this field. It deserves a separate course altogether if you were to cover it in more detail. Okay, and it interacts with a lot of areas, the reinforcement learning. Typical computer science, AI, machine learning, engineering, right? If you are designing a robot, a lot of engineering will have to go in. Neuroscience as well, mathematics obviously, economics and psychology as well. So it's a quite interdisciplinary area which has overlap with lots of areas. Okay. Okay, so let's look at it more carefully. What is, how do we formalize this setup of environment and agent? So let's say there's a set of states S of the environment. Let's say they are only finite. This is finite. So only finite number of states. Later you can think about infinite states as well, but for now let's just think of finite number of states. And there's a set of actions that can be performed, and we again assume that this set of action is also finite. Okay? So what happens at each time step? The agent senses the current state of the environment. Based on this, it chooses an action. And then based on the current state and the action, it gets a reward. So at time t, if the state is st and the action is at, it gets a reward which is both a function of the action and the state. And because of the action, the environment generates the next state. And that is given by this function delta, that if you are at current state st and the agent performs the action at, your next state would be st plus 1. Okay. So the key thing in this setup is that your reward that you get at each step, it only depends on the current state and the current action. It does not depend on the previous states, which is a very important assumption, right? That simplifies it a lot. And the next state that you get only depend on the current state and the current action. It also does not depend on the past. We can also model this delta in R as stochastic functions. So there could be, for example, a normal distributed random variable with a mean given by these functions. Right? This could be stochastic as well. But we'll start with the deterministic version. Okay? And let's say we know the reward function and we know the next state function also. Let's say these two things are known for the agent. Okay? Now, how would we choose the best policy? Okay, so before you go there, you have to define a policy. Okay. So, my task for the reinforcement learning agent is to learn a policy. What is a policy? It's a mapping from the state of the environment to the action. Because once I sense a particular state, the agent has to choose what action to take. And this action should be done in a way that we maximize the reward. Okay? So policy is a function of the present state in the environment, mapping it to an action. And what is the reward? Okay, so let's say the policy is pi. So V pi st. In state t, if you are in state t and you apply policy pi, what is your reward going to be? Your immediate reward is r of t that you give. But your future reward would be r of t plus 1 when you apply this policy pi. And next step reward will be r of t plus 2. We multiply these rewards with the scalar gamma, which is between 0 and 1. So this is what is called discounted future reward. Okay. So if gamma is 0.9, I give full weightage to the current reward. Then it is 0.9 times the reward at the next step, and then 0.9 square times the reward at the next step, and so on. Okay? So, V pi s of t is summation I is going from 1 to infinity, 0 to infinity, gamma to the power I, reward at step t plus I. Okay? So, how do I maximize now? Yeah. How do I maximize reward? If I knew everything, how would I maximize reward? If I knew the delta functions, how do I choose a policy? And the R function. Right? So, remember, what do I have? I have, let's say these are the set of states of the environment. You can think of it as a graph. So, and then from this state I can choose, right? So this is s of t, this could be s of t plus 1, and this is a reward here if I choose a particular action. And from here again, depending upon the action, you can go to the next states. Right? So let's say the rewards are known to me. This function, reward function, which is going to map a state and action to a real number, this is known to me. So in that case, how do I maximize the rewards? How do I choose a policy that will maximize the rewards? Okay, so let's say you are at a state st, okay, and now you are contemplating what action I should take. I can take action for any action. In the set of actions, I can take any action. So if I take an action A, then immediate reward would be R of st comma A, and then future reward is immediate reward. And what's the future reward? So I've already defined V pi st. So my future reward would be V pi. What is going to be the next state? Delta of st comma A. That is telling me the next state. So that's my future reward. No, wait. That is not my future reward. That is actually, so gamma times this would be the future reward, because it is discounted by gamma. Okay. So what do I do? Pick A that maximizes R of st comma A plus gamma times V pi delta st comma A. If I knew what V pi was, right? If at all I knew what V pi was, only then I could do that. And if you look at this formulation, here the time, it's sort of invariant about time. If I visit a particular state at time t versus t plus 10, that doesn't matter. Because if I start with that state, what is my discounted reward? And if I start with the state before, let's say st minus 1, then it will be a gamma times discounted version of the same reward, because everything is getting multiplied with gamma. Okay. So now if A that maximizes this, let's say A star is R max, is the optimal step that you take. Then what can we say? We can say that V pi star, the optimal policy, at st, right? The optimal reward that I will get at st would be what? Would be gamma st comma A star, the optimal step, plus gamma times V pi star delta st A star. Right? So if I knew okay. But if I don't even know ST, maybe I can, create a dynamic program and solve this. But how do I solve this if I don't even know this reward function? Right? So the Q learning algorithm gives a way to actually solve this problem in almost optimal manner, right? In asymptotically optimal manner. And how does the Q learning work? Basically, what it does is we create an estimate of this reward function at every state. In fact, we define a Q function. I'll just give a formal definition. So, yeah. So let's say Q S comma A is the reward that you will get if you start with state S and take the action A. So this is the immediate reward. And this is the discounted future reward. Right? Okay. Where, V star is the optimal, this is the optimal reward, right? This is the optimal reward. With the optimal policy. Okay. So how do we, so what is the algorithm? I'll tell you the algorithm, then we'll go over the proof. So the Q learning algorithm So if I knew Qs comma A, right, for every state if I knew the optimal, then I can just, pick up the optimal action A, just take an action that maximizes the Qs comma A, because this is the total reward. Okay. Total reward if at state S you take the action A. Right? And then what you can do, you can pick an action which maximizes Qs comma A. So if you can learn this function Q, then I can actually make my agent, give the optimal reward. So that is the basic idea, that how do we learn this function Q. So what we are going to do is maintain an approximation to Q, which we call Q hat, initialized, let's say, to 0. Right? We are assuming all the rewards are greater than 0, right? Greater than or equal to 0. So we are going to estimate this, initialize it to 0 at every step. So this is initialization. So now you repeat, select an action A Okay, let reward be R. I get a reward R. Let new state be S prime. Then what do I do? Q hat S comma A is the reward R plus gamma times max over A prime Q hat S prime comma A prime. Until convergence. So I initialize all the rewards to 0 and I arbitrarily select an action at a present state. Let's say I randomly select, right? Because I have to explore all the actions. I have to see all the actions, what the rewards will I get for each of the actions. And once I execute the action, I get a reward S, R, and the new state is S prime. Right? Now, how do I update the current estimate of the total reward I'll get? Immediate reward is R, that I have already observed. So I can update that. Right? And now I also know that it has gone to state S prime. So at S prime, I have an estimate of a lifetime reward for every action A prime. So if I was to take an action A prime which maximizes this future reward and discount it with gamma, that's my new estimate of the estimated reward using the optimal policy at S comma. Okay. Is the algorithm clear? Okay. Now it turns out I have not told you how to take an action A. But if you can pick this action A in a way that at every state you will pick every action infinitely often. So for example, first time I come to state 1, I pick action 1. Next time I come to state 1, I take action 2. So I just do actions in a round robin manner. Right? So then, every time if I visit this state infinitely often, then I would have also taken all the actions infinitely often. I can fix any order of these actions, and as long as I am guaranteeing that, I am going to take every action, large number of times, I can show that this algorithm will actually converge to the optimal value of Q. The Q hat will converge to the optimal value of Q. So that is the thing. If I choose my action, if I explore enough of the actions, and I keep taking those actions again and again, then it is going to converge to that. Okay. Shall we try to prove it? So, if we initialize Q to this, can we say Q hat to this? Can we say that Q hat S comma A is less than equal to Q of S comma A for all S comma A? This we can say, right? So what is my error? Let's say Q hat at time t is Q hat t S comma A, right? So error, let's call it delta at time t, or let's say error at time t. Error is Q hat t S comma A minus Q of S comma A, right? That's my error in a state S comma A, right? If I state S, I take action, that's my error. And let's say I do a max over this over a s comma a. Okay. So initially your q hats are 0. So initially in first step your error is the maximum value of q s comma a, right? The maximum reward that you can get, right? Maximum discounted reward. Now from this, if I visit every state at least once, starting with 0, what I can show is every state and every action at least once, right? Every action in every state at least once. Then I can show that, let's say that is a time step t prime. So at t prime, the Q learning algorithm visits every state and every action at least once after time step t. Right? Then what I can say, the error at time t prime is less than or equal to gamma times the error at time t. I'm looking at the maximum error at all the states and actions, that is I've defined error at t, and I start at time t. T could be 0 to start with. In that case the error would be the maximum q, and I claim that from this point, if the algorithm goes through every state and every action at least once by the time it reaches at t prime, then my error at t prime is reduced by a factor gamma, at least by a factor gamma. Right? So why don't you think about it and try to prove yourself. Maybe we'll prove it in the next class when we discuss it. The basic idea is this discounting factor, right? And at every step you are choosing the best approximation from the previous step. So using these two things, you can actually see what is your update rule. Q hat t s comma a at state s is gamma plus maximize a prime q hat s prime a prime, right? If you take action a at state s and you go to next state a prime or next state s prime, this is how you update q hat t, right? Now this part of the update is correct. This is the actual reward you get. This may be incorrect. Sorry, this is max of this, gamma times max of this, right? This may be incorrect. But this is going to be less than the actual one. And this is going to get diminished by gamma. That reward is actually diminishing by gamma. So the next step error that you are looking at q hat here is going to reduce by gamma. So therefore, this step error, the one that you updated, has become better. The error has become better by factor of at least gamma. So that's the basic intuition. And if you keep doing this over and over again many times, this is going to converge to the actual, gamma to the power some n times e of t. So it's going to converge that. So think about it. It is just a basic algebraic manipulation. If you just write the formulas, it will actually come out. So try to prove it yourself. Right? This could be a good exercise for the exams. Problems like this. Try to prove it. This is ungraded homework, okay? So, but don't look at the solution. I'm sure you can get solutions from outside, but just try to do it yourself once. Okay? So, yeah. And then we'll continue in the next class. Okay? Thank you.